Cool. Okay, so the next question that we got on the menu today is asking us, a horizontal force of 159 newtons pushes a 20 kilogram block up a frictionless incline that makes an angle of 35 degrees. I'm going to assume that A just means like degrees with the horizontal. Now, what is the normal force? Okay, well, before we even start asking questions about this situation, let's draw a diagram for this situation because just purely word descriptions are pretty tough to deal with. So I like drawing diagrams because they can really help us. Okay, so it's saying that we have a block on a frictionless incline. I feel like we can represent that pretty well with a triangle like this. Okay, looks pretty good. And we have a 20 kilogram block. Let's draw that. $20 kilogram block. Okay. And nice. And it says that we have a 159 Newton force that is perfectly horizontal. Okay, so it's not going to be on the same angle as the incline itself. It's going to be perfectly horizontal. So it's going to be something like this. So 159 newtons, whoops, not K, 159 N newtons, and we're also going to have, what's another detail? We have a 35-degree angle here. 35-degree angle, and let's actually draw a free body diagram of this situation, or let's draw like the other forces of interest here. So we know that this 20 kilogram block here, well, things are heavy, and with the power of gravity, they fall. Gravity will typically force you to fall because gravity is a force, and this 20 kilogram block is definitely going to have a weight force of gravity. So this would be like, let's call that W for weight is equal to mass times the gravitational acceleration. That's one of the forces that's also going to be on here. It mentions that the slope, the incline is frictionless, so we have no friction force. That's nice and convenient, one less force to worry about. But how come this block isn't falling through the ramp? It's because the ramp has a opposing normal force, and we have to consider that. And that's also the thing that we want to that's another thing that we want to solve as a part of this. The first part of the question is trying to tell us what is the normal force. Okay, I'm just going to draw that in a different color so it's very clear and distinct. And one interesting thing about the, oh, that's not a different color. One interesting thing about normal forces, so let's call that Fn for normal. They always have to be perpendicular to the surface. Okay, so this is perpendicular to a ramp. Which means it has a 35-degree angle from the vertical. So you see how the ramp has 35 degrees from the horizontal? Well, this one is 35 degrees from the vertical. You know, that's kind of a rule if things are perpendicular. Okay, so let's actually draw this free body diagram again, but like off the ramp. Okay, I'll do this in black. I can kind of imagine this as a particle. Yeah, okay, so here we have Fn. (35 degrees towards the right of the perfectly vertical, so this would be Fn. Here we have mg. And here we have our perfectly horizontal force of 159 newtons. Okay, now it might be a little bit more convenient if we put all of our forces in an axis that is like you know, along the slope. Okay, so if we have our x and y axes like this, this will make our calculations much simpler. It's still possible if we don't make an alternate axis. It's just going to be a little bit painful. Okay, so knowing this is our redefined axis, we know that our normal force is going to be perfectly in the y direction. So actually, I'll redraw this free body, or I'll make some adjustments to our free body diagram. So if this is our y direction, and this is our x direction, like that, just as it appears in the diagram, we could see that, well, we would have this situation here, and this angle here is 35 degrees, and this angle here is let me think about this for a moment. So let's do the angle like this, and we will have okay, so if it's perfectly horizontal and we want to resolve it up the ramp, we're gonna have this angle as 35 degrees. It has to be 35 degrees because pretty much what we have is like the force is like this, the ramp is like this, so this angle 35 has to be the same as this angle 35 up here. Okay, so that's pretty much where all of these angles come from. Okay, now we know that the force along the y direction of this situation has to be 0, the net force. And the reason for that is because, well, we know that it's only going to slide up the hill or down the hill. So with our tilted axes right here, we can only have x direction forces that are not perfectly neutralized. So if we wanted to do the sum of all y forces, we have to equate them to 0. If the y forces were not 0, it would be like lifted off or pushed deeper into the ramp itself. And we're gonna assume that like the ramp does not like curve or deform in any way that would allow things to be pushed into it. So we have to have a 0 y force. Okay, now what are our forces in the positive y direction? We have Fn, and there's no need to have any angle associated with it. Okay, now let's look at mg. Okay, so now mg is going in the negative y direction, so we got negative. We're going to have mg, and we're also going to multiply this by a factor of cos 35. Okay, the reason why is because we want the this component right here. So this is mgy and mg x. Okay, that's a little messy. I'll redraw that. Okay, so you see the actual mg, we could break it into components, and the components are related to our tilted axes. So we only want the y components of the mg. So to get that, we need to multiply in cos 35, which is about maybe 80% of it. Okay, and that seems fairly reasonable. Okay, now since our pushing force was perfectly horizontal, this is also going to be pushing it into the ramp a little bit. Okay, so there is going to be a y component to the perfectly horizontal force, and the y component is going to be sine 35. You see, like this is pretty much the same as saying this angle is like, or this force is something like this, something like this. Okay, so we only want the one that's along the y, and that's got to correspond to sine 35. Okay, so that's going to be, let's draw that in. minus 159 Newton times sine 35 degrees. Okay, awesome. So now let's sub in our m value. Our m value is 20 kilograms. And our g value is equal to 9.81 meters per second squared. I use 0.81. You could use 9.8, but here in Canada it's 9.81. Closer to the poles of the Earth, you'll have faster acceleration, and closer to the equator, you'll have slower acceleration. So you might, in your local area, you might have a different g value, but we'll just use 9.81 for here in Canada. Okay, cool. Let's sub these in. But first, let's isolate Fn, because that's going to be our target variable, actually. Okay, so Fn. And then we're going to bring these two terms to the other side. And let's sub in m and g. So we're going to have m is equal to 20 kilogram. Multiply that by 9.81 meters per second squared. Multiply that by cos 35 degrees. And we are going to also add, now it's going to be this term, so the 159 Newton term, but when we bring it to the other side, it's going to be positive. And I'm a positive guy, so let's put that in there. So we got 159 newtons multiplied by sine 35 degrees. Okay, and once we do this calculation, this will give us the normal force, and then that'll be one part of our question done. So let's set this in. So 20 times 9.81 times cos 35 degrees. Make sure your calculator's in degrees. If you do it in radians, big ouch, I'll tell you that. Okay, so plus 159 times sine of 35 degrees, and our final result here for the normal force is equal to 251.92 newtons. Okay, awesome. So this would be our normal force. Normal force on ramp. Awesome. Okay, so that is part A of this question finished. Super cool. Okay, now the second question is asking us what is the acceleration of the block. Okay, so this kind of ties into what we were doing previously. I'll actually I'll copy down this whole diagram so we don't gotta draw it in again, because what we're going to be doing here is we will be doing pretty much the same thing that we did with in the y direction of our tilted axes, but we're going to do it in the x direction. Okay, and that's going to give us a force, and then once we get that force, we can divide out the mass and find the acceleration up the ramp. Okay, so here let's paste that in. Okay, so this was our free body diagram of just the forces that correspond to our ramp situation up here. Okay, cool. So now we want to find, there is only a net force in the tilted x-axis direction. Cool. So how we're going to set up our equation is we're going to want to do something like this. Okay, so we want to have the sum of all x forces in here. Is going to be equal to the mass of the thing multiplied by acceleration in the tilted x-axis. Okay. Now previously we set up our equation differently, so the sum of all Fy was equal to 0, but that's because there's no acceleration in the y direction. Like if my arm is a slope, there's no acceleration this way. There's only acceleration this way. Okay, so that's why in the x direction there we're gonna have a ma instead of a 0, which is gonna be the sum of all the x direction forces. Cool. So let's take a look at all of our forces and see who has a x direction contribution. So Fn, Well, Fn is strictly and purely in the y direction. So that's going to have no effect on the x direction axes of force. Okay, so let's consider our gravity. So you see mgx, that appears to be, it's going to be mg, right? But we want only the x components about it. And that's going to be sine 35 degrees. Okay, you can kind of see how that works. Think back to your trigonometry. If you just want to get like a component from an actual force. Okay, so we're going to have, and that's in the negative direction, or that's going to be in the positive direction. So the way we set up our axis is we have positive down the ramp, negative up the ramp. Okay, so it's positive down ramp, negative up ramp. Okay, so you know, down the ramp, what's the weight going to do? Gravity is going to try to push you down the ramp, so it's going to be a positive. So it's going to be positive mg multiplied by not cos. In this case, it's going to be sine 35 degrees. And here we're going to have, now the second thing that we need to consider is going to be the 159 Newton force, perfectly horizontal. In this case, we want to get just the x component of it. This is going up the ramp though, so it's going to be a negative term, negative. And then we're going to have the 159 Newton. And what term do we have to multiply into here? Cos 35. Okay, and you can see kind of how the angle works. We want to get we have the hypotenuse and the angle. We're trying to get the adjacent. So with SOHCAHTOA, we can do it this way by doing cos 35. Okay, so let's isolate AX. AX, and M is equal to 20 kilograms. Yep. And G is still going to be 9.81 meters per second squared. And when we do this, we'll have AX equal to 1 over 20 kilogram. So that's 1 over M multiplied by 20 kilogram times 9.81 meters per second squared multiplied by sine 35. And this is minus 159 newtons. Multiply that by cos 35. Okay, and we'll ask our calculator what this is, because mental math is tough. Okay, so we're going to have 1 divided 20. 1 divided by 20, and that whole thing is multiplied by 20 times 9.81 times sine of 35 degrees. And that whole thing is subtracted by 159 times cos 35 degrees. Close those brackets. And my final acceleration calculation for this is negative 1.61 meters per second squared in the x direction. Now keep in mind, we've said that negative is going up the ramp and positive is going down the ramp. So this is going to be up the ramp. So with the given forces, the block will accelerate up the ramp at 1.61 meters per second squared. Okay, that's going to be our final answer, and that resolves the second part of our question, and that's the final part of our question, so we can call it a day. Okay, Now, I think I've seen a question questions similar to this in like my first year of university or first year of college when I was doing engineering. So, it is fun stuff. It is fun stuff. They're just like the main key here is that you want to set your coordinate axis to be along the ramp and then resolve your horizontal and gravity forces to be along those tilted axes. It's going to be way more difficult to try to do it with like a regular XY being like perfectly horizontal, perfectly vertical. That's going to be way harder. Okay, so there's no above solution. Is no given solution. Okay, cool. So yeah, that question, that's that.